the classification of crystalline, classification of crystalline solids. The first is covalent crystals. This first of all, this classification is mainly based on the constituent particles or the force, the difference in the type of force that binds the constituent particles. If you suppose if it is atoms that are binded, then with what type of bond? If it is molecule or if it is ion, or how it is, how the constituent particles are binded to one another. This is what is this is on which it is the classification is based. For example, as we have seen, now this is first crystalline solids, the covalent crystals. Covalent crystals means the basic point is it is the intermolecular force, that is binding force. The binding force is covalent bond. The binding force is covalent bond. As the binding force is covalent bond, now the molecule or the crystal as a whole may be conducting or non-conducting. For example, you take the case of graphite, diamond. These are the best examples of covalent crystals. In the graphite, the constituent particles are in both graphite and diamond. In both graphite and diamond, the constituent particles are carbon atoms. Now, in both graphite and diamond, as you know very well that in graphite the carbon atoms are sp2 hybridized, and in the diamond carbon atoms are sp3 hybridized, and there exists a covalent bond. But as you know that graphite is good conductor, but whereas diamond is non-conductor, right. So, like this, but in both graphite and diamond the binding force is covalent bond. It is a 4 orbitals, 4 electrons in the valency shell that will involve in the bonding, right. Here the carbon atom, other 4 carbon atoms are attached like this, and here it is hexagonal structure in the case of graphite. This is what is covalent crystal means. The next is the what you call molecular crystal. In the case of molecular crystal, so now second is molecular crystal. In the molecular crystal means constituent particles are molecules. Constituent particles are molecules. Like in the case of ice, it is water molecule. In the ice, the constituent particle is molecule, that is water molecule. Then dry ice, the constituent molecule is carbon dioxide. As you know very well that in ice the binding force is hydrogen bond. The binding force is hydrogen bond. So, like this in every molecular crystal, either hydrogen bond or dipole-dipole interactions, van der Waals force. Like this, different types of physical forces. In the molecular crystals, the binding force is the physical force like hydrogen bond, van der Waals force, ion dipole interactions, dipole-dipole interactions, any of these sort of physical forces will exist. And again this molecular crystals may or may not be conductors, right. That depends on how the arrangement is, right. This is molecular crystal. Then next we will see about ionic crystals. Third one is ionic crystal. In the ionic crystal, the constituent particles are ions, and the binding force is the what do you call Coulombic forces of attraction. It is the force of attraction, Coulombic force or interionic force. It is the force of attraction between two oppositively charged ions. For example, sodium chloride crystal, cesium chloride crystal, right, or ZnS, CaF2, so on and so forth. And we have many types of crystals that all we discuss in future, in the coming lectures. In all this, one ion is attached to different other ions, how they are arranged and all that in the crystalline structures we are going to discuss. But definitely all the ions are due to strong Coulombic forces, all ions are strictly attached to their particular positions like this. The lattice will be like this. So, as a result what happens is neither any ion nor any particle like electron or proton are able to move along the crystal lattice. So, these are not conductors. Pure crystalline solids are not conductors. And the melting and boiling points are also, very high for them. Melting points are high. They will possess, crystalline solids possess high melting points and they are non-conductors. This is about ionic crystal in brief. Of course, more about ionic crystals what we are going to discuss in this chapter now in the coming lectures. Then next what we have is another type of crystal, that is interstitial crystals, right. In this interstitial, now in the interstitial crystals is what we are going to see now. Metallic crystals. Is more important. Metallic crystals, the particles are metal atoms and the binding force is metallic bond. The binding force is metallic bond. For example, sodium metal, potassium metal, gold, zinc, iron, copper, so on and so forth. In all this, different sodium atoms are held together in sodium metal lattice, different number of potassium atoms are held together, copper atoms are held together in a copper metal. So, in this the bond is metallic bond. The metallic bond again we explain in different ways, that is also we consider as a covalent bond, one type of a particular covalent bond where the free ions of the metal, free electrons of the metal will form a pool and will move along the vacant orbitals and will form a strong attractions between one atom and the other atom. So, these are the metal atoms are the constituent particles and the metallic bond is a intermolecular force, that is a force that binds each metal atom together, and all metallic crystals are conductors. all are very good conductors. So, the reason for the conductance of the metallic crystals is there exists a large number of free electrons. The very basic point, the very basic characteristic property of the metal is to have unpaired electron and free vacant orbitals. Due to the presence of unpaired electron and due to the presence of vacant orbitals, all the unpaired electrons of each metal atom will have free space to move, and so they will move from one atom to the other and will be keep moving in the entire lattice. As a result, they are good conductors. This is a basic classification of crystalline solids: covalent solids, molecular solids, ionic solids and metallic solids. The interstitial solids, of course, that makes that interstitial solids is not necessary to be considered as separate, because that is interstitial solids are formed due to the defect in the crystal. Sometimes in the vacant spaces some foreign atom will get embedded. That in the defects we discuss about this, how different foreign atoms will occupy the interstitial solids and what difference in the properties due to this occupancy, which results in stoichiometric and non-stoichiometric defects. That is entirely a separate thing, but that is not necessary to be considered under classification, but definitely that also makes certain difference as far as the classification is concerned. But that will come under again part of each and every this major classification. So, this comes to the now completes the classification of crystalline solids. The next is, in the crystalline solids, what are the different types of arrangement in which this atoms or molecules or ions can be arranged, and for any crystalline solid, first of all, what are the basic physical parameters we have to discuss. First, what is the related terminology? Here the whole arrangement of atoms or molecules or ions in any of the crystalline solid is what we call crystalline lattice. Then what is crystalline lattice? What is unit cell? What are the different types of unit cells? This all now we discuss.